Alright, so here's part 2 of my presentation on nuclear fusion and reactors. As I said before, one does not simply fuse two nuclei. You can't just take two single proton atoms and put them together and make a helium. You just can't do it that way. It's not that simple. As you can see in the graphic here, we have a positively charged proton here and a positively charged proton here, and as I said before, these two things both repel each other. So, a tiny little bit of math here. As we know with electromagnetic forces, they are related to 1 over r squared, r of course being the distance between the two charged particles. So as r gets to be really small, this force becomes really, really big. And to overcome this, these two atoms have to be moving really fast. They have to have a very, very high amount of kinetic energy in order to get close enough so that the nuclear strong force can take over and overpower the electromagnetic force. An example of fusion, which is all of you are familiar with, is the sun. The sun is powered by fusion of light elements. The sun itself is 15 million degrees Celsius at the core, and I was supposed to copy down the notes here. Anyway, most of the matter in the universe is created by nucleosynthesis, which is what happens in stars. It's fusing two light nuclei together to form a single heavier nuclei. For example, as we've covered before, the deuterium, which is 2H, and the tritium, which is 3H. If you fuse those two together, you have helium and one free neutron. This can also be done with iron or any other elements. You just fuse two nuclei together and you have a third new element. So, as I covered before, fusion creates energy. So, as technology develops, we're requiring more energy to sustain our society. And if we could control fusion, we could make electricity. And the great thing about fusion energy is that it's totally safe and environmentally friendly, because the only byproduct you get from fusion is helium, which is everywhere and is completely environmentally safe. Ask a clown. What I mean by safe as well is that nuclear fusion, unlike fission, is not a chain reaction. So if we want to stop fusion, we just change a tiny little setting and fusion is done. It will never get out of hand, and yeah, it's totally safe. Unfortunately, we have had some scientific and technological hindrances. I'll get onto those in a few minutes. However, progress has been made, and there is a due date, an estimated due date, which I will talk about in a little bit as well. So there are two kinds of reactors that I want to talk about. The first is inertial confinement fusion reactor. The process of inertial confinement fusion itself is basically just you have these little pellets here. These little pellets are very small. Oops, sorry. Damn it. These little pellets are very small. They're made out of tritium and deuterium, which is the fuel source I was talking about before. And the process of inertial confinement fusion is we take a bunch of lasers and we direct them at the surface of this pellet. Now this pellet superheats on the very surface and eventually will explode. And there will be an outward explosion, and as we know with Newton's third law, for every action there's an equal and opposite reaction. So, with the explosion outward, we will also have a force inward, which will cause the core of the pellet to superheat and superpressurize. And if we can get it just right, fusion will occur. And once the fusion starts right in this core here, it will spread to the outside of the pellet, and the thermonuclear energy will consume the rest of the pellet. This process is called ignition, and it's basically once fusion happens in the center, it's self-sustaining. The fusion will happen all the way through the core, from the core outward. So ICF reactors will supply a steady stream of these fuel pellets, and by a steady stream, it's usually a few every second. The resulting heat from this fusion is captured and converted to electricity, similar to a steam engine. There are some problems, though. Since this process does involve lasers, and the process first started back in the 1970s, lasers were very inefficient back then, and the power required for just the lasers to heat the pellets was it's not enough. In order for the fusion to actually happen, they had to power the lasers with more power than was produced by the fusion itself. So the gain, which I'm not sure exactly what the 350 times is, I think it's just an arbitrary gain here, is 350 times just to break even. Currently, our best ICF or IFC reactors only give about, actually it should be ICF. I can't believe I haven't changed that again. But anyway, the current ICF reactors only get about 100 times gain. So we're about 250 times off gain still. But progress is being made and lasers are being improved every day, so don't give up hope. The second type of confinement reactors is magnetic confinement, which I find to be very fascinating. Not that I don't find inertial confinement fascinating, but the magnetic stuff is really cool. So in the 1960s in Moscow, there was a design called the tokamak, which stands for toroidal chamber with magnetic coils. This is an acronym. It's actually Russian, so that's why the words in the acronym don't match up. It's because it's translated. But a toroid is a ring shape, and I'm guessing you can figure out what a chamber and what magnetic coils are. Instead of heating pellets, the fuel, which is still the deuterium and tritium, is heated and kept in a ring shape, and it's heated up to a plasma, which a plasma is it's just free electrons and superheated neutrons, ionized neutrons. And when this gets to just the right conditions, fusion will happen. And when the fusion happens, as I said before, there's the free neutrons that escape, and the free neutrons have about 80% of the energy, of the fusion energy. So these neutrons are completely immune to the effects of the magnetic confinement. And I forgot to mention that the magnetic confinement keeps the plasma from touching the walls of the chamber. But the neutrons are not charged, so the magnetic fields don't affect them. So the neutrons will escape from the magnetic field and collide with the walls of the chamber. And then the walls of the chamber will heat up, and that heat will be converted to electric energy as well, also similar to the steam engine. So as you can see, the process itself is really simple from a conceptual point of view, but once you get down to the nuclear physics of it, it's actually quite complicated. So that concludes the second part of my presentation. Stay tuned for the third.